Hello, everyone. My name is Youwei, and I'm a postdoc working at the University of Virginia. So today, my topic is a bit simplified compared to my abstract. So how do braided channels migrate? I guess many of you have seen presentations about channel migration in meandering rivers by tracking the like the channel center line, but braided channels also migrate, and they also matter. So they can influence the landscape evolution. People living beside would be influenced by braided channel migration. They also impact the sedimentology, like they can influence the bar reworking. They together with channel erosion can determine the stratigraphic architecture. And also from the source to sink perspective, they can impact the sediment storage and release. So it is very important, but compared to the meandering rivers, it's still not well studied. And today, so I'm going to use a method called PIV, so particle image velocity. So this is a new method introduced by Austin Chadwick just in this year. And so its principle is to compare a pair of images. So a pair of images to see the difference between them. Yeah, so like here, so you can see this is a photograph at time t. On the right, you see t plus delta t. So the dashed lines indicate the difference between these two images. Then you can see how the channels migrate. You can know the migration, basically the displacement and also direction. So this method was using on satellite images, also from data, but they are mostly on the photographs. So my supervisor has a data set of the topography in the St. Anthony Fall Laboratory. This is a very large dimensional film. It's like 70 meter long and nearly 3 meter wide. So this offers an opportunity. So such a long distance can suppress the boundary effect as a basin inlet and also the outlet. Then on the right, I show the topography. So the red is the bars, then the blue is the thread, is a channel threads. So with this kind of data set, we hope we can extract channel motion over time and also over space. So the PIV method requires feeding of the images, like binary images. So we first have to convert this topography data to binary image. So on the top, I show the topography. You see the blue indicating channel thread, the red indicating bars. Then by thresholding the elevation, we have the binary mask. You see the white indicating channel threads, black indicating bars. So we find that there are still many noise, like measurements of artificial noise. So we use a median filter to make the edges between the bars and channels like sharper. So overall, we are satisfied with this conversion. Then, okay, so in this data set, it's a very typical classical data set that evolves from a from a straight channel. Then, so first you have the incipient meandering. Gradually, the meandering turns into braided phase. Then in the last stages, so the morphology is very stable. So it's almost like a mature. So we roughly have 3 phases in this data set, and later you may see the corresponding consistency between them. Okay, so here we show how the PLV performs in tracking channel motion. On the top, you see the binary mask. You see how the channels migrate, and then in the sorry, I have a unknown call. Right. Yeah. So here, yes, below you see the migration vectors at different space and also over time. So here I summarize the vectors. You can see that many of the vectors seem to cluster as a curvature. So like those places, then it's natural to speculate whether the curvature also play a very important role, like meandering river migration. So now I show the detailed spatial temporal variability of the channel migration rates. So this kind of heat map, you see so the axis is the downstream distance, while the y-axis is the time. So you can see that, and the color indicates the migration rate, with red indicating higher rate, blue indicating lower rate. And you can see that if we look at this direction, we see how it evolves over time. It roughly seems like it first increases a bit, then constantly decrease. While over this direction, you see how the channel migration rate varies over space. And they are high and lows, and you don't really see a trend like constant growing or constant decreasing. So let's zoom in to the time series first. Let's look at this direction. And here is like the cumulative probability. You can see that so the time is dark at 0, then lighter in the 19 hours. So the channel migration rate first increased from 0 to 5 hours, then keeps decreasing over time. So this is how we find it varies over time. Then we look into the spatial series. We take example of t equals 6 hours. So here you can see the spatial series from upstream to downstream. And here I use different moving windows to average the migration rate. So my PhD was about cyclostratigraphy. So when I see those peaks, oh, they are cycles. So they are repeating patterns. So naturally, I apply the time series on the spatial series. So it's very funny. Time series on the spatial series data. Then we found that there is a significant peak at 1.1 wavelength. And then we can say that there's some repeating pattern in space, like every 1.1 meter, you may have similar curves, you may have similar migration rates. So below I show the elevation map and also the vectors. Here the scale bar is 2 meter. So now my guess is it might be the case the half meander. I mean in one meander you have two like peak and valley. Then those curvature driven might be also responsible for the migration rate. So another term called confluence difference spacing might be similar to the half meander wavelength in this context. Okay, so in this data set, there are 4 runs, and now we look at the impact of discharge and slope on the channel migration rate. Overall, so this is upstream, this is downstream. So we find that lateral migration much outweighs the downstream of upstream migration in all the 4 runs. So we're still working on the dimensionless framework to compare the 4 runs, and that's now ongoing. And my take-home message is the PIV is very efficient in fetching channel motion. With time, migration rates first increase and decrease. With space, there are some quasi-periodic variations. And the last thing is lateral migration outweighs downstream, upstream migration in all the runs. Okay, thank you.